So we are passing on to the second example on motion of, analysis of friction of connected bodies. So in this case, I have given you a numerical example. I'll give you the question. I will read: two blocks A and B weighs 500 Newton and 1000 Newton, and they are placed on an inclined plane. The blocks are connected by a string parallel to the inclined plane. Coefficient of friction between the inclined plane and block A is 0.15, and that for block B is 0.4. Find the inclination of the plane when the motion is about to take place. Also calculate the tension in the string. Block A is below the block B. So it is illustrated in the figure. There are two blocks A and B. First one is 500 Newton and B is 1000 Newton. They are resting on an inclined plane. Say theta. The inclination of the plane is say theta. They are connected by a string. So they are connected by a string which is parallel to this plane. So this is an inclined plane. They are connected by a string. The coefficient of friction between inclined plane and A. So the coefficient of friction for this first body, mu A, is 0.15, and coefficient of friction between the body B and the inclined plane, mu B, is 0.4. So the coefficient of friction, it depends upon the surface roughness and the configuration of that block B. So these two values are different. You are asked to find the inclination of the plane, find theta when the motion is about to take place. So they are at rest now in an inclined plane. When the motion just starts, that is called the limiting equilibrium. When the motion impends or when the motion just starts, what should be the inclination of the plane? So we have seen earlier also, as long as the inclination is small, they will repose on that or stay back on that plane. But as the inclination is increased, there is a point when the body slides down. That particular value of angle is known as angle of repose. So we have to find out what is theta here. So what, as usual, we have to consider the two bodies separately and draw the free body diagrams. Mark all the forces. Isolate each body from the other one and mark the forces acting on them. First, I will consider block A. Block A is resting on this inclined plane. So its self-weight is marked vertically in the gravitational direction. And if theta is the inclination of the plane, angle between the normal to that and normal to the inclined plane and vertical, this angle will also be theta. Always remember it. If to an inclined plane, the value of angle theta is given with horizontal, angle which the normal to that plane makes with vertical, that will also be theta. So I can resolve W into two components. W along this axis, it will be cos theta, and perpendicular to the axis, it will be sin theta. Okay, the two components of theta, W cos theta, H W sin theta. The normal reaction of the surface, the normal reaction acts vertically in this direction, perpendicular to the surface. Normal reaction acts perpendicular to the inclined plane. And there is tension in the rod. The tension in the string, tension will always act away from the center. So tension we have marked. So here we have marked. First of all, we have marked the self-weight and marked the two components along the plane and normal to the plane. Then the normal reaction between the inclined surface and the body, RA, tension in the rod acting away from the center, parallel to the inclined plane. What else remains? When the body is moving down, the direction of motion is this. This is the direction of motion. If it moves down, the friction force will be acting opposite to that. So the frictional force, it is equal to mu times RA. Here I will mark it as mu A RA because mu A is having one value and the other one is different. So these are the forces acting on body A. Now consider this. We can resolve it. I'm going to, because most of the forces, all the forces are now along the plane and normal to the plane. So I'm going to consider the x-axis along the plane and the y-axis normal to the inclined plane. So resolve all the forces along the plane, resolving or considering the equilibrium along the inclined plane, resolving all the forces, resolving the forces along the inclined plane, and I am going to write sigma fx is equal to 0. Sigma fx is equal to 0 means what are the forces in the x direction? In that direction t acting in the positive direction, then mu Ra also acting in that direction plus mu A is 0.15 Ra, the frictional force, mu A Ra, two forces in that direction, W sin theta in the opposite direction. So minus W sin theta, that is 500 sin theta is equal to 0, that is one equation. Now considering sigma Fy is equal to 0, resolve the forces normal to the plane, considering the forces normal to the plane, Ra minus 500 cos theta, W cos theta is equal to 0. So from this I will get Ra is equal to 500 cos theta. Now this value I will substitute in 1. Put Ra in 1. The value of Ra in 1 will get T plus 0.15 into 500 cos theta minus 500 sin theta is equal to 0, or we get T is equal to 500 sin theta minus 0.15 into 500 is 75 cos theta. I will get one value for T. Now let me consider the free body diagram for the second one. For the bottom block, I have considered already now. I am going to consider the free body diagram of block B. So block B, as A moves down, B will also move down. So the direction of motion of B is also downwards. So considering block B, the self-weight acts in the gravity direction. Self-weight W 1000 Newton acts in the vertical direction. I have resolved it into two components. If this is theta, angle between the normal to that and the vertical is also theta. So W sin theta along the plane and W cos theta normal to the plane. Now the reaction, the contact reaction RB, perpendicular to the surface RB. Tension in the rod T, away from the joint. As it moves down, the frictional force mu RB, it is mu B RB, because mu B is having a value 0.4. So mu B RB will be opposing the motion. So these are the various forces acting on this body. Now let me consider the equilibrium of forces. Sum of all the horizontal forces is equal to 0. Consider the forces along the plane, and let me write sigma fx is equal to 0. You are considering sigma fx is equal to 0. Only mu B RB is acting upwards. Mu B is 0.4. 0.4 RB minus T minus W is 1000. Minus 1000 sin theta. Consider the free body diagram of B by writing sigma fx is equal to 0. Mu B RB, that is 0.4 RB, T acting downwards, so minus T minus W sin theta, 100 sin theta is equal to 0. Now let us write sigma Fy is equal to 0. Considering vertical equilibrium, sigma Fy is equal to 0. Forces acting upwards, RB, this W cos theta acting downwards, minus W cos theta is equal to 0, or RB is equal to 1000 cos theta. Now in this expression we have RB as well as T. So substitute for T from here. This expression and RB from equation 4. So from equation 3, this equation 3 will be converted as 0.4 into 1000 RB cos theta, 1000 cos theta, 0.4 into, instead of RB, we are putting 1000 cos theta, minus T. T is here, 500 sin theta, minus 75 cos theta, minus 75 cos theta, minus 1000 sin theta is equal to 0. So this equation 3 we have substituted for RB and T from these two expressions. From that can rearrange all these terms and finally you will get 475. Clubbing the terms of cos theta and sin theta together, we will get that is equal to 1500 sin theta. So from these you can write tan theta is equal to sin theta by cos theta. Tan theta is equal to 475 divided by 1500. That is, here I am going to write, this is sin theta. Sin theta by cos theta is equal to 475 by 1500. 1500 sin theta equals 475 cos theta. So tan theta equals 475 by 1500. Hence we get theta is equal to 17.59 degrees. That was the first question. What is the inclination of the soil? I mean inclination of the plane, so that when the motion is about to take place. What is the inclination of the plane? So inclination of the plane is equal to 17.59 degrees. The next one is find tension in the spring. To get the tension in the spring, so this is the expression for tension in the spring. T is equal to 500 sin theta minus 75 cos theta. In this expression, put the value of theta 17.59. By putting the value of theta in that expression, so what we have to get is T. Put the value of theta in this expression. T is equal to 500 sin 17.59 minus 75 cos 17.59 will work out to 79.61 Newton. So whether it is problem on a horizontal plane or an inclined plane, whether they are single body or connected body, any type of problems in the analysis of friction can be solved by drawing the free body diagram of the bodies and applying the equations of equilibrium. So next we will see an application of the bodies on inclined plane we have seen now. An extension of this can be used for solving the analysis of problems on wedges. So next we see wedge friction. Thank you.